core, and it literally consists of two different processes. Okay, so let's see if I can find. There's basically two things that are going on when we talk about oxidative phosphorylation. Okay, so we've got all at this point, we've done glycolysis, we've done pyruvate oxidation, and we've done Krebs cycle, right? So all the energy in the glucose from the first three stages is now in either NADH or FADH2. That's where the electrons are. That's where the energy is from sugar. What we need to do now is convert the energy in the electron carriers to ATP. Okay? So what we're going to do is we're going to use these electron carriers, right? We have these three electron carriers, these ones we talked about the other day. And we're going to have NADH and FADH2 dump their electrons onto these protein complexes. Okay? When they do those redox reactions, or maybe I'll do it over here. Every time this NAD passes electrons onto this protein, okay, and then this electron moves to the next part of the electron transport chain, an H plus is moved from the mitochondrial matrix to the inner membrane space. Okay, so since there are three proteins that go across the membrane, the electron, when it passes through, will move hydrogens across 3 times. That's the oxidative part. Now we have to talk about phosphorylation, which is making of the ATP. By pumping hydrogens across here, we have more hydrogens on this side, less hydrogens on this side. So there's a hydrogen gradient to come back in. The only way the hydrogens can get through this lipid bilayer is by passing through this enzyme, ATP synthase. Every time hydrogen passes through this enzyme, the enzyme will grab an ADP and phosphate and turn it into ATP. That's phosphorylation. Okay? So what we've done, we've taken the energy of the electrons in an electron transport chain, used that energy to move hydrogen across the membrane space, creating a hydrogen energy gradient. That hydrogen gradient then is used to synthesize ATP from ADP and phosphate by using ATP synthase. This part is the oxidative, this part is the phosphorylation, and the creation of the gradient is called chemiosmosis. And that's the process. Okay, you still sound confused. What part are you not getting? Okay, you're taking ADP and phosphate, right? So my blue balls represent, these blue atoms represent the phosphates, okay? And in order to make, this is ADP, in order to make ATP, I have to take this and attach it like that, okay? Well, that's exergonic, it requires energy, okay? Because this has less energy than this. So in order to get this to join here, I have to use energy to get that to join. Okay. So what's my energy source? My energy source is going to be this hydrogen ion gradient. I'm going to use hydrogen pumping through this enzyme to force these two molecules together. Right. So if I go to, hang on YouTube, and go to ATP synthase. Yeah, this is
high school. I'm going to tell you guys a bit more about Grammarly. So what the application provides is in-depth
Concentration gradients are a key component of the biological world. The potential energy from these gradients is often used to perform biological work. Here we will focus on hydrogen ion concentration gradients. Hydrogen ions are also known as protons. A gradient exists when there is a higher concentration of a molecule in one compartment compared to a neighboring compartment. This animation will demonstrate how the potential energy that results from a hydrogen ion gradient uses ADP and inorganic phosphate, also known as PI, to synthesize ATP. This process involves an enzyme complex called ATP synthase. Gradients and the potential energy they create are key aspects of the biological world. A good example of the use of a gradient occurs in the mitochondria when ATP is synthesized. ATP is synthesized by ATP synthase, a large complex of membrane-bound protein. Here we see ATP synthase, along with other membrane-bound proteins. Notice the large difference in the number of hydrogen ions on the two sides of the membrane. This difference is a hydrogen ion, or proton, concentration gradient. The energy associated with this gradient is used to synthesize ATP from ADP and PI. This occurs at the ATP synthase complex. One hydrogen ion enters the ATP synthase complex from the intermembrane space, and a second hydrogen ion leaves it on the matrix space. The upper part of the ATP synthase complex rotates when a new hydrogen ion enters. Once 3 protons have entered the matrix space, there is enough energy in the ATP synthase complex to synthesize 1 ATP. In this way, the energy in the hydrogen ion gradient is used to make ATP. Now let's watch the process again. Notice how the proton enters the ATP synthase and exits into the matrix space. Once 3 more hydrogen ions have crossed the membrane, another molecule of ATP will be made. In this example, the hydrogen ion gradient is large enough to produce 6 ATP molecules. Please watch as the remaining ATP molecules are synthesized. The process has now completed, and the result is an equal number of protons on each side of the inner membrane. Without a gradient, there is no more energy available to make ATP. In biological systems, however, a gradient is always maintained. The mitochondrial hydrogen ion gradient is generated as electrons pass through 3 membrane complexes. That process can be seen in the mitochondrial electron transport chain animation.
Did that help? Okay, so it doesn't matter if we're talking about mitochondria or chloroplast, as long as you've got a hydrogen, because the ATP synthase is the same in both situations. As long as you've got more hydrogen on one side than the other, then that ATP synthase will continue to work and make ATP. So the oxidative part of this is that we need those electrons from NADH to go through that electron transport chain so that the hydrogens keep getting pumped out so that we have a concentration gradient maintained. If that concentration gradient ever balances, ATP synthesis stops. Okay? And that's the basic issue, is that so let's see if I can find that as well. Okay, so maybe that one. Yeah, okay. So let's see if this tab.
The electron transport chain is a series of protein complexes embedded in the mitochondrial membrane. Electrons captured from donor molecules are transferred through these complexes. Coupled with this transfer is the pumping of hydrogen ions. This pumping generates the gradient used by the ATP synthase complex to synthesize ATP. The following complexes are found in the electron transport chain: NADH dehydrogenase, cytochrome BC1, cytochrome oxidase, and the complex that makes ATP, ATP synthase. In addition to these complexes, two mobile carriers are also involved: ubiquinone and cytochrome C. Other key components in this process are NADH and the electrons from it, hydrogen ions, molecular oxygen, water, and ADP and PI, which combine to form ATP. At the start of the electron transport chain, two electrons are passed from NADH into the NADH dehydrogenase complex. Coupled with this transfer is the pumping of one hydrogen ion for each electron. Next, the two electrons are transferred to ubiquinone. Ubiquinone is called a mobile transfer molecule because it moves the electrons to the cytochrome BC1 complex. Each electron is then passed from the cytochrome BC1 complex to cytochrome C. Cytochrome C accepts each electron one at a time. One hydrogen ion is pumped through the complex as each electron is transferred. The next major step occurs in the cytochrome oxidase complex. This step requires 4 electrons. These 4 electrons interact with a molecular oxygen molecule and 8 hydrogen ions. The 4 electrons, 4 of the hydrogen ions, and the molecular oxygen are used to form 2 water molecules. The other 4 hydrogen ions are pumped across the membrane. This series of hydrogen pumping steps creates a gradient. The potential energy in this gradient is used by ATP synthase to make ATP from ADP and inorganic phosphate. The ATP synthesis steps you see here are discussed in greater detail in the ATP synthase gradients animation.
Okay, so that's why you have the electron transport chain, because the electron transport chain makes the hydrogen gradient, and the gradient runs ATP synthase. Okay, I'll put those 2 animations onto the onto Google Classroom as well then. All right, I hope that clears things up. Okay. Yeah, have a good weekend.